probably not going to be as good as the ones already out there. But a lot of times you do need to write your own game engine if you're trying to create your own style of game, and there's something out there that you can't use it for. Most large game companies will have their own proprietary engines that they'll write, and then they'll just use it over and over and over. All right. As I mentioned before, game engines, it's kind of a fuzzy term, but there's a lot of engines within a game engine. There's physics engine. Down here, a couple popular physics engines are PhysX by NVIDIA. They wrote a physics engine that is the backbone physics of a lot of the engines that are in the industry. There's a Havoc physics engine, which is used in the Elder Scrolls series. Ogre 3D is a rendering engine. That basically means a graphics engine, so you don't have to worry about any graphics. So you can actually use some of these pre-built components in your own engine, and you won't have to worry about writing those components from scratch either. Now to a little more detail on rendering engines. If you wanted to write a rendering engine from scratch, and you wanted to write a 3D rendering engine, you're going to need to probably use a platform-dependent API. I don't know if any of you guys have heard of DirectX, which is Microsoft Platform Graphics API, basically, is the most simple way to put it. And then there's OpenGL, which is a cross-platform industry standard. It's open source. Anybody can use it. Both of those are widely used in the game industry. You kind of have to make a decision on which one. I mean, I'll go over both of those later. But you'll generally want to make a decision on which you want to use to write a rendering engine. To get started with 3D programming, though, I would suggest Ogre 3D. It's kind of a wrapper. It encapsulates the functionality of DirectX and OpenGL. It'll give you a lot of the abstract ideas of 3D programming. But once you get down to it, if you're asked to write a 3D rendering engine, you're probably going to need to know both OpenGL and DirectX. Okay. All right. As I said, rendering, just think graphics. It's the software process of basically data that's input into your rendering engine or your rendering application, and your program is expected to produce primitives, which make up models, and models make up the scenes in your games, which are basically what you see in the game is a bunch of models, a bunch of meshes that are rendered to the screen from data that comes from somewhere else, whether it be mesh files or even text files. Obviously, it's the most apparent aspect of game development. Actually, when you launch your game, the first thing you're going to see is the graphics. All right, a little more specifically, there's a lot of subtle details in graphics programming, or in rendering engines in general. A lot of the cool lighting effects that you'll see, shadows, reflections, environmental animations, particle effects, terrain generation. There's a lot inside the rendering engine. It's considered by a lot of people to be the most important aspect of the game engine is how good is your rendering engine? What kind of performance can you get out of your rendering engine? You want the best graphics, the most computations possible to be done at a very high performance. You want it to run on as many platforms as possible. You don't want to have high standards for your hardware. My favorite part about writing rendering applications is that even though I'm not like the biggest fan of math, it's really rewarding when you get to use some differential equations or calculus or a lot of the stuff that you learn in physics, fluid dynamics. You can use all this stuff infinitely. You can do anything you want basically once you've learned this technology. Like if you learn how to use DirectX or even XNA, which a lot of you will if you participate in the workshop. You can, if you see in Calc 3, you'll see how to build an ellipsoid, and you're like, oh, that's great, and then you can answer a question. But you can graph the function of an ellipsoid, and you'll see it constructed. And once you've done it right, you'll see it constructed. You can manipulate it. You can build any kind of function you can think of. You can do random functions which produce terrain generation. It's really a really rewarding field. It really kind of concretes what you learned in college in your engineering degree. Graphics programming. This is a lot larger field than a lot of people tend to think. When you say graphics programming, a lot of people tend to think game technology, which probably is the forefront of graphics technology. But you'll see it a lot in animated films, Avatar, Kung Fu Panda. All that is graphics programming. There's a lot of graphics programming that goes into it, but that's not what people would consider real-time graphics programming. Real-time graphics programming is video games. You have to be able to render multiple frames per second as opposed to 1 frame per week. You'll see graphics programming behind modern medical devices, AutoCAD, local picture of AutoCAD, scene rendered there. And you can pretty much do anything you want with graphics programming. You can make any graphical application for anything you want. Interfaces are graphical applications. If you look at job applications for basically any company that needs an interface done, one of the requirements will be that you know a 3D API or assembly for the graphics cards that they need. So yeah. All right, one of the probably the biggest part of graphics programming is knowing shaders. Shaders are written in their own language, which might sound a little intimidating, but it's basically C. There's a few syntax differences. There's a lot more functionality built into it than C. But the most common shader languages that you'll see in DirectX and XNA, you'll be using HLSL, which is high-level shader language. OpenGL uses GLSL, and NVIDIA wrote their own high-level shader language called C for graphics. It's designed to work with both DirectX and OpenGL. As the name indicates, it's basically C.
Does Safety I have one as well, or no?
I'm not sure.
I've never
I don't think so. All right. There are 3 kinds of shaders that you can write. I don't know if I went over this, but shaders are programs that will run on your graphics card. Most of the programs that you guys have probably written, definitely all the ones you've written at USF, run on the CPU. They're instructions that are executed by the CPU. You don't even touch the GPU, which is definitely more powerful than the CPU in a lot of aspects. Shaders are little programs, sometimes big programs, that you write to be specifically designed to run on the GPU. You take advantage of hardware acceleration on the GPU. Basically, functionality, you can access it through shader programs that you write. The first step in the rendering pipeline, which I'll go over probably later, but the first shader that your data goes through is a vertex shader. It runs for each vertex in the scene. So say you have a little cube in your scene. If that's all you wanted to draw in your scene, you would have 8 vertices, and you would have to program each of the positions of those vertices. If you didn't use like 3ds Max or Maya to import the vertex data, you'd have to manually position each vertex. You'd have to give it you'd have to give it texture attributes. That's all details, but it all gets fed into your vertex shader from your application code, from your C++ code. Vertices will be streaming into your vertex shader. The calculations that you customize in the vertex shader will be performed on each vertices. Normal calculations for lighting and shadows, texture coordinates. So if you have a texture of a square and you want it textured on the front face of your cube, you need to define texture coordinates within the vertex shader. A lot of transformations, rotations, translations, and scaling is all done in the vertex shader. So if you want a rotating cube, you'd put like a sine function inside your vertex shader for each vertices, and it would rotate all of your vertices appropriately. The geometry shader is actually pretty new. Within the last couple of years, it was developed, and it's available with DirectX 10 and up. And within the geometry shader, you can create entire primitives. It takes, instead of streams of vertices, it'll take, say, a stream of 3 vertices for a triangle, depending on what primitive you define. It'll take an entire triangle, and you can do whatever you want with that. A good example of geometry shading is billboarding. And billboarding is, if you have a large 3D scene, say you have a big valley of trees, it would be really wasteful to generate the primitives and the data for each of the trees, the 3D models of the trees. Instead, what they'll do is they'll literally just put a point for where that tree is, just a little dot, and in the geometry shader, from the dot, they'll create a rectangle in the geometry shader, and then they'll put a picture of the tree on the billboard. It's called billboarding, and that point will always face the camera. So from far away, it'll look like you have a tree that's 3D because the picture is always just rotating. And really, in your program, all it is a little dot that in the geometry shader gets expanded, texture gets applied, and it always follows the camera. And that saves a lot of calculations, a lot of useless 3D calculations that you would have to do otherwise.